Good morning all. Skillage Centre for Economics in the മറ്റൊരു വീഡിയോയിലേക്ക് സ്വാഗതം. കഴിഞ്ഞ ക്ലാസ്സിൽ നമ്മൾ ഡിസ്കസ് ചെയ്തിരുന്നത് മൾട്ടിവേരിയേറ്റ് ഫംഗ്ഷൻ എന്നുള്ള ടോപ്പിക് ആയിരുന്നു. മൾട്ടിവേരിയേറ്റ് ഫംഗ്ഷൻ്റെ ഡെറിവേറ്റീവ് എങ്ങനെയായിരുന്നു കാണുക എന്നുള്ളതായിരുന്നു. അതിൻ്റെ ആപ്ലിക്കേഷൻസ് നമ്മൾ എക്കണോമിക്സിൽ ഡിസ്കസ് ചെയ്തു. അവിടെ മൾട്ടിവേരിയേറ്റ് ഫംഗ്ഷൻ ഓപ്റ്റിമൈസ് ചെയ്യുന്ന സമയത്ത് ദി തേർഡ് ഓർഡർ കണ്ടീഷൻ നമ്മൾ ഡിസ്കസ് ചെയ്തിരുന്നു. അതിൻ്റെ തേർഡ് ഓർഡർ കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യുക എന്നുള്ളത് വളരെ ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള ഒരു ഘടകമായിരുന്നു. അതിൻ്റെ ഫലമായിട്ട് ആ തേർഡ് ഓർഡർ കണ്ടീഷൻ നമുക്ക് എവിടെ നിന്ന് കിട്ടി, ആ കണ്ടീഷൻസ് എസ്പെഷ്യലി നമ്മൾ ഡിറൈവ് ചെയ്തിരുന്ന കോൺസെപ്റ്റുകളെയാണ് ഇവിടെ നമ്മൾ ഇന്ന് പരിചയപ്പെടുത്താൻ പോകുന്നത്. സോ ബിഫോർ വി ആർ ഗോയിങ് ടു കൺസിഡർ അനദർ ടോപ്പിക് ദാറ്റ് ഈസ് ഓപ്റ്റിമൈസേഷൻ, എസ്പെഷ്യലി ദി കൺസ്ട്രെയിൻഡ് ഓപ്റ്റിമൈസേഷൻ. See, we have one topic which is known as special determinants. There are certain metrics concept which are very much related to the optimization of a multivariate function. These special determinants or metrics are Hessian determinant, higher order Hessian determinant and bordered Hessian determinant. കഴിഞ്ഞ UGC JRF NET എക്സാമുകളിൽ ഇതുമായിട്ട് ബന്ധപ്പെട്ട ഒരുപാട് ക്വസ്റ്റ്യൻസ് ചോദിച്ചിരുന്നു. അതുകൊണ്ടാണ് ഞാൻ ഈ ടോപ്പിക് ഇവിടെ കൺസിഡർ ചെയ്യാനുള്ള പ്രത്യേകിച്ചുള്ള കാരണം. സോ വി ആർ ഗോയിങ് ടു ഡിസ്കസ് ഹിയർ വാട്ട് ഈസ് ആക്ച്വലി ദി Hessian matrix is when we are using Hessian matrix and higher order Hessian and similarly the bordered Hessian as well. So the first we are going to consider the Hessian determinant or Hessian matrix. See what actually the Hessian matrix means. See, first we are considering here a multivariate function. As earlier also we discussed here, z is the function of x and y, where z is the dependent variable and x and y are the independent variable. Of course we have more than one independent variable, that's why we are saying that it is an example of a multivariate function. In order to maximize a multivariate function, we are discussed various conditions as well. See, for the relative maximum we said that the first order derivative, first we have to take the first order derivative. The first order derivative, partial derivative with respect to x, with respect to y, then that should be equate with 0. Then we have to find the critical point. So the first step was the z of x, that is partial derivative with respect to x and partial derivative with respect to y, we have to calculate. Then the second condition was for the relative maximum, the second order partial derivative, the second order direct partial derivatives, that is z of xx into z of yy, both are less than 0. And for ensuring the relative maximum situation, we have the third order condition as well, that is z of xx into z of yy should be greater than z of xy all square. That means the product of direct second order direct partial derivative should be greater than the second order cross partial derivatives. So these were the conditions of relative maximum, especially for finding the relative maximum. Then we have another was relative minimum also. For finding the relative minimum, we have to take the same steps, that is first we have to take the partial derivative with respect to x, then partial derivatives with respect to y, then that first order partial derivative should be equate with 0 so that we can solve that particular equations and ultimately we will get a values for the x and y, and these values are generally known as the critical values. So this is the first order condition, that is first order partial derivatives should be equate with 0. Then after that we said that the second order direct partial derivatives should be greater than 0. What are the direct partial derivatives? Z of xx and z of yy, both should be greater than 0. And the third order condition is same as in the case of a relative maximum, that is z of xx into z of yy should be greater than z of xy all square. So we have this particular equation, or in another way the third order condition we can say that z of xx into z of yy minus z of xy all square should be greater than 0. Both are equal. ഇത് രണ്ടും സെയിം ആണ്. ഒന്ന് നമ്മൾ ഗ്രേറ്റർ ദാൻ പെർട്ടിക്കുലർ ക്രോസ് പാർഷ്യൽ ഡെറിവേറ്റീവ് പറയുന്നു, ഇവിടെ ഇത് തമ്മിലുള്ള വ്യത്യാസം ഗ്രേറ്റർ ദാൻ 0 ആണ്. ബോത്ത് ആർ ഈക്വൽ. ഓക്കെ, നൗ ദിസ് കണ്ടീഷൻ, തേർഡ് ഓർഡർ കണ്ടീഷൻ, അല്ലെങ്കിൽ ഈ z of xx into z of yy minus z of xy all square എന്നുള്ളത് എവിടെ നിന്ന് വന്നതാണ്? ആൻഡ് ഇത് ഓൾറെഡി ഡിറൈവ്ഡ് ചെയ്യുന്ന ഒരു പ്രത്യേക മെട്രിക്സ് ഉണ്ട്. ആ മെട്രിക്സിന് പറയപ്പെടുന്ന പേരാണ് Hessian matrix. So I am introducing here the Hessian matrix. See, I am denoting in terms of this is Hessian determinant. H is denoting for the Hessian. It is Hessian determinant. See, it is a square matrix. Of course, it is a square matrix of second order partial derivatives of a function. See, what are the elements of this given particular matrix? In the given Hessian matrix, the elements are the second order partial derivatives. What are the second order partial derivatives? We have two direct partial derivatives and we have two cross partial derivatives. So here it composed of, this particular matrix composed of second order partial derivatives with second order direct partial derivatives will be on the principal diagonal and the second order cross partial derivatives on the off principal diagonals. So for example, if you are going to write, that is, this is Hessian determinant. Hessian determinant is equal to, see, the z of xx. What is z of xx? It is second order partial direct partial derivative, then second order cross partial derivative, second order again cross partial derivative, second order direct partial derivative. We are defined here the Hessian determinant as, see, it composed of second order direct partial derivatives on the principal diagonal. Direct partial derivatives are z of xx and z of yy. See, on the principal diagonal, this is the principal diagonal. In this principal diagonal, we have the second order direct partial derivatives. Then after that, see, on the second order cross partial derivatives, what are the second order cross partial derivatives? Which is z of xy, z of yx, both are in the off principal diagonal. This is the off principal. This is principal diagonal. This is the off principal diagonal. Now, we have a determinant here. See, z of xx, z of xy, z of yx and z of yy. This is the actually Hessian determinant. Now, if you take the determinant value, this matrix value, then it is nothing but we can say that it is Hessian determinant value. See how we are going to find the determinant? The product of diagonal elements minus the product of principal diagonal elements. See, the product of principal diagonal. What is the product of principal diagonal? That is z of xx into z of yy minus the cross partial derivatives. That is z of xy into z of yx. So I am writing here, see, since z of xy is equal to z of yx, how? As per the Young's theorem, we class discussed, as per the Young's theorem, the cross partial derivatives are equal. That is z of xy is equal to z of yx. We can write it is the partial derivative, the determinant value, that is Hessian determinant, is equal to the z of xx into z of yy. That is the product of the direct partial derivative, that is z of xx into z of yy minus z of xy into z of yx. Since z of xy is equal to z of yx, we are putting it is both are equal, so we are putting into the square term. So minus z of xy all square. This was nothing but it was the third order conditions for unconstrained optimization when we have a multivariate function. So Hessian determinant was used. Hessian determinant use when we have an unconstrained optimization. We have a given multivariate function. We want to optimize the multivariate function. Then the third order condition which is required for especially the optimization, that is nothing but this z of xx into z of yy minus z of xy all squared. That is the product of direct partial derivatives should be greater than the cross partial derivatives. This particular formula which we are actually derived from the Hessian matrix, or this value is nothing but it is the Hessian determinant value. So this is the actually Hessian determinant is. So Hessian matrix is nothing but it is composed of all the second order partial derivative where the direct partial derivatives are given on the principal diagonal and cross partial derivatives are taken on the off principal diagonal, and its determinant value is nothing but it is the third order condition for the optimization, especially when we are going to consider unconstrained optimization. Unconstrained optimization, constrained optimization at that particular point of time we will discuss what actually the constrained optimization. Okay, so this is the Hessian determinant. Now see how to interpret the results on the basis of Hessian determinant. See, if the first element on the principal diagonal, that is first principal minor. What is the first principal minor? That is generally denoted as H1. It is denoted as H1, that is first principal minor, that is the first element of the Hessian matrix. Hessian matrix first element aanu first principal minor എന്ന് നമ്മൾ denote ചെയ്യുന്നത്, that is H1, that is Z of XX is greater than 0, and second principal minor, that is H2. What is the second principal minor? That is H2, that is the given Hessian matrix value. Hessian matrix value or determinant value is greater than 0, then this is the condition for the second order condition for the minimum. So when we have an optimization problem, especially unconstrained optimization, then the second order condition for the optimization, especially for the minimum, we have a condition that the H1 is greater than 0, and at the same time H2, the determinant value of 2, that is also greater than 0. Then this is the condition for the minimization condition. Now let us take the Hessian matrix, that is first principal minor Z of XX is less than 0, and at the same time H2, that is greater than 0. The first principal minor which is less than 0, and at the same time this value is greater than 0, the determinant value of Hessian matrix is greater than 0, then this is nothing but this is the second order condition for the maximum. So actually this is the third order condition and this is also third order condition, but H1 is nothing but this is the second order condition, especially if you look at this Z of XX is greater than 0, that means first principal minor is greater than 0, then this is the condition for minimum. If the Z of XX, that is first principal minor, is less than 0, then this is the condition for the minimum. Let us take one example. See, we have an optimization problem, that is we want to optimize this given function, that is Z is equal to 3x square minus xy plus 2y square minus 4x minus 4y plus 12. See, in order to optimize this particular function, we have to satisfy certain conditions. Of course, we have a first order condition, second order condition and third order condition as well. See, the first order condition is nothing but we have to take the partial derivative with respect to x and with respect to y, then it should be equate with 0, and accordingly we have to find out the values for x and y, and these values are generally known as the critical values. See here, I am taking the first order partial derivatives here. See, the first order partial derivative with respect to x, the derivative of 3x square, which is equal to 6x, the derivative of xy, by keeping the y term is constant, the derivative of x is equal to 1, so 1 into y, which is equal to y. Then we have, this is y term, we have x term, that is minus 4x, the derivative of minus 4x is equal to minus 4, and then this is y term and this is constant. So we have 6x minus y minus 4, which I am equating with the 0 and denoting in terms of equation number 1. Similarly, z of y. See, z of y, that means we are going to take the partial derivative with respect to y. See here, this is x term, here it is y term, so we are going to take the partial derivative with respect to y. So the derivative of y is equal to 1, so 1 into x, which is equal to minus x. Then here we have a y term, 2y square, the derivative of 2y square is equal to 4y. This is x term, we have the derivative of minus 7y, which is equal to minus 7. I am equating with the 0 and putting this is the second equation. Now, see here, after finding first order partial derivatives, see, we want to solve this equation simultaneously so that we can find the unknown values for the x and y. See, we have a two variable x and y. This is an example of a simultaneous equation. If you solve the simultaneous equations, then of course we will get the values for x and y. For that, I am rearranging this equation, especially for the solution purpose. Taking the first equation, 6x minus y, taking minus 4 into the right side, so it will become plus 4. So it is 6x minus 4, which is, minus y, which is equal to 4. That is equation number 1. And for the equation number 2, it is minus x plus 4y, which is equal to 7. So by taking these two equations, see, we have a simultaneous equation, and these two simultaneous equations, we have a two unknown variables as well, that is x and y. But in order to solve this particular equation, we are using an elimination method, and for eliminating here, for example, I am going to eliminate here the variable x. In order to eliminate the variable x, the coefficient of the variable x should be same, but here the coefficient of x is here 6, here the coefficient of x is equal to minus 1. So I am going to make the coefficient same by multiplying the equation number 2 into 6, so that the coefficient of x can be similar. See, 6 into minus x, 6 into 4y is equal to 7 into 6. It will become, see, first equation I am writing as it is. The second equation I am multiplying with the 6. So it will become minus 6x plus 6 into 4, which is 24y, which is equal to 7 into 6, which is equal to 42. So this is equation number 3 I am denoting. Now see, we have the variable x have the same coefficient, that is 6. I am going to add this particular equation so that we can remove the variable x. So now we want to eliminate the variable x. In order to eliminate the variable x, I am adding these two equations, so that 6x plus minus 6x, which will become cancelled out, then minus y plus 24y, which is equal to plus 23y, 4 plus 42, which is equal to 46. So y is equal to, it is 46 divided by 23, or dividing the both side of the equation by 23, it is equal to 46 divided by 23, which is equal to 2. So y is equal to 2. Now we are going to substitute y is equal to 2 on the any one of the equation. For example, I am going to substitute on the equation number 1. The equation number 1 is equal to 6x minus y, which is equal to 4. Substituting y is equal to 2, it will become 6x minus 2, which is equal to 4. 6x is equal to 4, taking minus 2 into the right side, so it will become plus 2. 6x is equal to 6, and x is equal to 6 divided by 6, which is equal to 1. So the value of x is equal to 1 and the value of y is equal to 2. And these are the critical points. X is equal to 1 and y is equal to 2. So these are the critical point. So after finding the critical point, see the second order condition, that is z of xx, z of yy, that is direct partial derivatives and cross partial derivative we want to find out. Now I am going to take the second order direct partial derivatives. See, the second order direct partial derivatives are z of xx and z of yy. See here, z of xx is equal to, I am going to take the partial derivative of zx with respect to x. We have a 6x here, the x term is 6x. I am going to take the partial derivative of 6x. So the derivative of 6x is equal to 6, which is greater than 0. Similarly, another direct partial derivative, which is z of yy. So z of y again with respect to y, so 4y, the derivative of 4y is equal to 4. See, z of xx and z of yy, these are the direct partial derivatives, both are greater than 0. See, in the case of a Hessian matrix, as I have already told you, if H1, that is Hessian determinant 1, that is nothing but the first principal minor, that is z of xx, which is greater than 0, then which will ensure you the condition for minimum, that is second order, the first principal minor H1, that is nothing but it was z of xx, which is 6, okay, which is greater than 0. So this is the condition for minimum, but also we have to consider the H2, the determinant value H2. So that is the Hessian determinant. So that we are going to consider. Before that, we have to take the cross partial derivative, that is z of xy and z of yx. Z of xy, that is I am going to take the partial derivative of z of x with respect to y. So here minus y, the derivative of minus y is equal to minus 1. Similarly, z of yx, this zy with respect to x, minus x, the derivative of minus x is equal to minus 1. Of course, as per the Young's theorem, the z of xy and z of yx both are equal, so which is minus 1. Now, after finding all these steps, see, it of course z of xx is nothing but it was, see, I am writing this z of xx and z of yy, z of xy and z of yx, that is the second order direct partial derivatives and cross partial derivatives. I have written it separately, which we are already calculated. See, H1, that is Hessian determinant 1, that is the first principal minor of the Hessian matrix, that is z of xx. First Hessian determinant matrix first element z of xx z of xx denote that is H1. If z of xx is greater than 0, this is the condition for minimum, but in order to ensure that condition, we have to take the H2, that is Hessian determinant 2, that is the determinant value of this particular matrix. So here z of xx, I am substituting these values. Z of xx is equal to 6, z of xy which is equal to -1, z of yx which is equal to -1, and z of yy which is equal to 4. Now you have to find the determinant value. So if you go for finding the determinant value, that is 6 into 4 which is equal to 24 minus -1 into -1 which is equal to 1. So -1. So 24 minus 1 which is equal to 23, which is greater than 0. So H2 is greater than 0, then it is the condition for function is minimum. See, the first condition, that is H1, that is greater than 0, and this H2, if it is also greater than 0, then the function ensuring that the given function is the minimum function. Okay, so in this way we can explain what actually the Hessian matrix and what actually the Hessian determinant is. Hessian matrix, once again I am repeating, it is nothing but it composed of the second order partial derivatives of a function, and the second order partial derivatives, the direct partial derivatives principal diagonalum, adipole thanne cross partial derivatives of principal diagonalum അടങ്ങിയിട്ടുള്ള ഒരു matrix ആണ് actually Hessian matrix എന്ന് പറയുന്നത്. അതിന്റെ determinant value കണ്ടെത്തി കഴിഞ്ഞാൽ ആ determinant value വെച്ചിട്ട് നമുക്ക് ഈ ഒരു optimization of function നമുക്ക് ശരിക്കും അത് optimize ചെയ്തുകൊണ്ട് അത് ഏത് രീതിയിലുള്ള function ആണ്, minimization ആണോ maximization ആണോ എന്ന് നമുക്ക് അംഗീകരിക്കാൻ പറ്റും. ഇവിടെ h1 greater than 0 ആണ്, h2 greater than 0 ആണ്, the function is said to be minimum. Now if h1 is less than 0, അगर h1 less than 0 ആണ്, അങ്ങനെ h1 less than 0യും h2 greater than 0 ആണെന്നുണ്ടെങ്കിൽ the function is maximum. Okay, that was the function maximum. But here the h1 is greater than 0 and h2 is also greater than 0. This is the condition for minimum.